Okay, so are there any questions before we start? Okay, so last time we were talking about the Lie bracket and Lie derivative of vector fields. So we saw that the Lie bracket of two vector fields is equal to the Lie derivative Lxy of y with respect to x. Okay, and that's defined to be ddt at t equal to 0 of the pullback phi t star of y, where phi t is the flow of x. Okay. And using this, we could show that the bracket is 0, identically 0, if and only if the flows of x and y commute. Okay. So the bracket gives a measure of how far the flows of x and y are from commuting. Okay, so any questions about this? Okay, so if not, then let's start the next topic, which is differential forms. So first of all, let's denote by Tp star m the dual of the tangent space Tpm. And then we can form, like the tangent bundle we took to be the union of the disjoint union of all the tangent spaces at points P and M. Similarly, this dual space Tp star m, this is called the cotangent space at P. And the disjoint union of these cotangent spaces is defined to be the cotangent bundle. Okay. And similarly, for any k, we can look at the kth wedge of the cotangent space and then take the disjoint union of these kth wedges of the cotangent spaces. That would be the kth, well, what would it be called? The kth wedge of the cotangent bundle. So these are called bundles. So maybe I should just make a remark that these cotangent bundle, tangent bundle, kth wedge of the cotangent bundle, all of these are examples of what are called vector bundles over M. So are you all familiar with the definition of a vector bundle? Should I recall? What is a vector bundle? Yes, anyone?
So I know the definition of vector bundle.
Yeah, so
So let me just briefly recall. So a vector bundle consists of a pair. Let's say a vector bundle over a smooth manifold. It's given by a smooth map of manifolds, a surjective map of manifolds, pi from E to B, where B is called the base and E is called the total space. And the idea is that E is a collection of k-dimensional vector spaces parameterized by points of the base. So suppose this is the base. And so then above each point in the base, you have a vector space. Okay. So E is a collection of vector spaces parameterized by points of the base. And so in each vector space, there is a zero element. So the collection of zeros passes through E like this. It's called the zero section of E. And what you want is that this collection of vector spaces is what is called locally trivial. So that means locally it's diffeomorphic to a product. So that means near any point in the base, I will have a neighborhood U such that if I look at the preimage of U in the total space, so that's the collection of vector spaces lying over points in U. So this would be pi inverse U. Then from pi inverse U, I have a diffeomorphism, say phi, which goes to U cross RK, okay, such that if I take the projection onto the first coordinate, so say, let me call that P1. So that maps U cross RK onto U. And here I have the projection pi from pi inverse U to U. Then this diagram commutes. Okay. So what does that mean? That means that the fiber over a point X here. So this is say pi inverse X. This is a k-dimensional vector space. This maps to the fiber over X in U cross RK, which is singleton X cross RK. All right. So phi of pi inverse. So this phi is a diffeomorphism. So phi of pi inverse X is equal to singleton X cross RK for all X in U. Okay. And what we want is that this collection of, so this phi is called a local trivialization. So on the right-hand side, this singleton X cross RK, this I can identify with RK itself, which is a vector space. So RK is a vector space. So the vector space structure on RK, I can induces a vector space structure on pi inverse X. And what I want is that this vector space structure on the fiber, pi inverse X, is independent of the choice of local trivialization. So if I have two local trivializations, say phi and psi, from pi inverse U to U cross RK, and to U cross RK. Okay. Then this map here is of the form x comma v goes to x comma. So a priori, the second coordinate here, this vector would be some function g of x comma v, right? This change of charts would be of this form, right? But what we want is that this change of charts is linear in v. So actually we want this to be of the form some smooth matrix valued function g of x into v. Okay, so where g here is a map from u into GL K R, which is a smooth map. Okay, which is called the transition function of the bundle, of the vector bundle. Okay, and the point is, because this transition function is linear, right? If I use the first trivialization to define a vector space structure on the fiber, that gives me the same vector space structure as if I use the second trivialization to define a vector space structure on the fiber pi inverse x, right? Because the change of charts is linear, right? So the vector space structure is preserved by this change of charts. So it doesn't matter which trivialization I use to define a vector space structure on the fibers, right? So therefore, for all x in x, for all x in B in the base, pi inverse x has a natural vector space structure. It's a real vector space of dimension k. Okay, is this clear? This is the definition of a smooth bundle. Yeah, any question? Okay. And associated to once you have a vector bundle, so I mean, just example, a vector bundle could be trivial. It could be a product. So for example, if I take my base to be a circle, the vector bundle, if I take it to be a product, then this product will be a cylinder. So this is called the trivial bundle, right? If I take a product, I'll just get a cylinder. Okay. So this is one possible vector bundle over the circle. And can you think of another possible vector bundle over the circle, which is non-trivial?
So you turn that line like you move around this circle and just rotate the arrow,
Right. So,
like
so what is that called?
the Mobius bundle.
Right. It's the Mobius strip, right? So you take this line and you twist it around and then you glue it back, right? So you get the Mobius strip. Okay. So these are both vector bundles over the circle. But these two vector bundles are distinct as vector bundles. Right? This one is locally, the Mobius strip is locally trivial, but not globally trivial. Okay, it's not globally trivial. I mean, it's not globally a product. So,
Each every vector bundle is locally trivial. I mean, locally
course,
it's a
of course.
product.
Yeah, sure. Locally, I mean, by definition,
Yeah.
vector bundle is locally trivial.
Sir, I have a question. This
Yes.
transition function, is this embedded? I mean, is this information there in the definition only? I mean, this linear thing?
Yes. Yes.
I have a confusion. That's what I'm asking. That's why I'm asking.
Yeah.
It is always okay there in the.
Yeah. I mean, see, what you have normally is you have a collection of
Local trivializations.
charts, which are an open cover of the base, U alpha, together with
Yes.
trivializations phi alpha from pi inverse U alpha to U alpha cross RK. Okay.
Hmm.
And on the intersection of two of these charts, you have a transition function G alpha beta.
Yeah.
Okay. So this maps to GLK R.
Mhm.
This is a smooth map.
Yes.
Okay.
Hmm.
And in fact, the collection G alpha beta is enough to define a vector bundle.
Vector bundle, yes.
It contains this collection G alpha beta.
Mhm.
This contains all the information about the vector bundle.
Mhm.
Okay. So
Right.
this is equivalent to the
You mean there are certain co-cycle conditions? That's what you're saying.
right, exactly. So it satisfies the co-cycle conditions. So G alpha beta into G beta alpha is identity.
Hmm.
And also G alpha beta, G beta gamma, G gamma alpha. Okay.
Yes.
So once you have this transition function satisfying these co-cycle identities, then you can define a vector bundle using them. All right. Right. The vector bundle would be basically you take the disjoint union of U alpha cross RKs, and then you quotient by the natural equivalence relation. Right. Is it clear?
Yes.
Yeah,
Yes.
you glue them along U alpha intersect U beta cross RK, right?
Yes. Yes. Right.
Okay, so yeah. So E is the same as the disjoint union of U alpha cross RK modulo the equivalence where XV in U alpha intersect U beta is identified with X G alpha beta X V. So, well, okay, U alpha, okay, well, U alpha across RK, this, U alpha intersect U beta cross arc. Is this clear?
Yes.
Right? Okay. Yes. Okay. Okay. Fine. So, so the one notion we need is what is a section of a vector bundle. So this is, so I have my vector bundle. And then what I do is I have my base, and a section is a map from the base to the total space, such that for each point below, say X, I choose a vector S of X in the fiber above. Okay, so this point would be S of X. So this belongs to pi inverse X for all X in B. Okay. Is this clear? Yeah.
Yes.
Okay. And this would be a smooth map of manifolds. Yeah. So now we can, in this language, we can say that, for example, Tm over M, the tangent bundle, this is a vector bundle of rank n, where n is the dimension of n, right? And similarly, once you have one vector bundle, then you can, just like given a finite dimensional vector space, say V, you can construct new vector spaces from it by various operations, such as the dual space, the kth tensor power, and the tensor powers of the dual and wedge products of the dual, and so on, right? So similarly, fiber-wise, you apply those operations and you can construct new vector bundles from a given vector bundle. So similarly, the cotangent bundle, this would be given by taking pointwise the dual of the tangent bundle. So this is also a vector bundle of rank n. Okay. And what is a section of the tangent bundle?
So smooth vector field.
It's just a vector field, right? So sections are just vector fields. Okay. And now a section of the cotangent bundle will be called a one form. Okay. So a section of the cotangent bundle, this will be called a one form. So what is a one form? That would mean that it's a map omega from M to T star M, a smooth map. Such that omega P, this is an element of the cotangent space, Tp star M for all P in M. Okay. Right? Now we know that given a chart pi, equal to x1 to xn, we know that this gives us a basis del del x1 up to del del xn of the tangent space at each point in the chart. So phi is from U subset of M to Rn. And we know that if I look at these functions x1 to xn, these are smooth functions on U, then their derivatives, their differentials dx1 to dxn, at each point, those give the dual basis, right, to the cotangent space. Okay. So this is the dual basis of TP star M. All right. And so any omega, therefore, omega at P will be therefore some linear combination of the dxi's. So it will be some AI of P, summation AI of P dxi, right? Because these are a basis of the cotangent space. Okay. Yes.
Yes.
Okay. And omega smooth means that the AIs, these functions are smooth functions. Okay. All right. Yeah, because I mean, the trivialization here is basically, see, for what was the trivialization for the tangent bundle? It was basically P comma summation alpha I del del xi maps to P comma the vector alpha 1 to alpha n. Right, this is my trivialization of the vector bundle, right? Okay. And similarly for the cotangent bundle, the trivialization would be P comma summation AI dxi. This maps to P comma the vector A1 to AM. Is this clear?
Yes.
Okay. So to say that omega is smooth means that phi composed omega is smooth. So that just means that the coefficients A1 to AN are smooth. Is it clear?
Yes, sir.
Okay. All right. Now, so what's an example of a one form? So example, if I take F is a smooth function on M, then DF, this is a one form, right? Because at each point P, DF at P, that is a linear function from the tangent space TPM to R, right? Yes?
Yes.
Yes.
Okay. We have DFP goes from TPM to R. So DFP belongs to TP star M. And we saw last time that if we want to write DFP in terms of the dual basis DXI, then DFP is nothing but summation del F del XI at P into DXI, right? Yes?
Yes.
Okay. All right. So this is a natural example of a one form. Now, similarly, we can look at differential K forms. So what are differential K forms? So first, what is the kth wedge of the cotangent space? This is the same as the space of alternating K multilinear functions, right? On the tangent space. Okay, so this is, we had a notation for this. This would be MK TPM R, right? So at each point, we have a P. We have this vector space wedge K TP star M, whose elements are functions of K vectors in TPM, which are multilinear and alternating, right? Oh, sorry. So this is not all of MK. This is, well, okay, fine. So, well, I didn't give a notation for this. Anyway, so this is a subspace of MK. Yeah, it's a subspace. MK TPMR is the full tensor product of TP star M. This is a subspace of that, right? Okay. Yeah. So, so we have the kth wedge of the cotangent bundle. So this will be the disjoint union of these kth wedge of the cotangent spaces. So this is a vector bundle over M. And what is the rank of the vector bundle? What is the rank? What is the rank of this vector bundle? Anyone?
N choose K?
N choose K, right? Yeah, N choose K. It's a vector bundle of rank N choose K. Okay. So here K I'm only taking between 1 and N, all right? I'm just taking K between 1 and N. For K bigger than N, this is 0. I mean, these kth wedges are 0 for K bigger than N. So I'm just taking K between 1 and N here. Okay. All right. So again, if I have a chart, well, okay. So a section, oh, so what first, what is a section? It means that at each point I will have a alternating K multilinear function on the tangent space. Okay, so by definition, a differential form of degree K on M, this is defined to be a section of this wedge K T star M. Okay, so that means let me so we can add sections pointwise, right? Since sections take values in a vector bundle. Okay. Since sections take values in a vector bundle, we can add sections pointwise, right? So yeah, there's one notation which is useful, which I forgot to mention. Yeah, the space of sections. So therefore, the sections form a vector space, right? Okay. And so the space of sections is usually denoted by gamma of E. Okay. All right. So for example, here for vector fields, the space of sections gamma of Tm is the space of vector fields chi m. Right? Okay. Yeah.
Yes.
Okay. So we will denote by omega km the space of sections, the space of K forms on M. Okay. Okay, so let's stop here and we'll start another meeting. All right. Okay. Okay, so we have the space of K forms on a manifold, omega Km. Okay, so omega Km is nothing but the space of sections of wedge K T star M. Okay. Gamma of wedge K T star M. Okay. And so now, what do differential K forms look like in a chart? So then we have a basis EI equal to del del xi of TPM. We have the dual basis EI star equal to dxi the dual basis of TP star M and so we know from the linear algebra which we did earlier that the basis of the kth wedge of TP star M will be given by k-fold wedge products of the dual basis elements, EI1 star, wedge, EIK star, right? Okay, so this is DXI1 wedge DXIK, where the I1 to IK is a multi-index in increasing order, strictly increasing order. So this is our natural basis of wedge K TP star M. So if omega is a K form on M, then on U in the chart, we can write omega pointwise as a linear combination of the basis elements, right? So this will be a sum over multi-indexes, I1 to IK in increasing order. Some coefficients A, I1 up to IK of P, DXI1, wedge, DX, IK, right? Where these functions A, I1, IK, again, these are smooth functions on U, right? Okay.
Yes.
All right. So this is what a K form looks like locally. It's a linear combination with coefficient smooth functions of DXI1 wedge DXIK. Okay. All right. So I'll just use a compact notation for this, just to make it simpler. So I'll write this as sum over I bar. Okay, where I bar is a multi-index in increasing order. All right. And these coefficients I'll write as A I bar. And this wedge product, this I'll write as DX I bar. So this DX I bar means this K-fold wedge product, DXI1 wedge up to DXIK. All right. Okay. So this is just a compact notation for this. Okay. All right. So these are what K forms look like. So we've already looked at the example of a one form, which is the differential of a function df. That's a one form. And so when we were doing the linear algebra of wedge products, and alternating tensors and so on, we talked about pullback of tensors and pullback of alternating tensors. So we can, given a map, a smooth map between manifolds, we can do this pullback pointwise, given a K form omega on in the range n, you can pull it back under the smooth map phi to get a K form phi upper star omega, which is a K form on M. Okay. So how do you define the pullback? Well, in the natural way. So say here is M and here is N. And so here I have an omega, which is a K form on N. So I want to pull it back to get a K form on M. So what do I do? At each point P and M, I have to define an alternating K multilinear function. So what I do is, given K tangent vectors, V1 to Vk at P, I have my map phi, which sends P to phi of P, and the derivative d phi at P. This is a linear map from TPM to T phi P n. So I can apply this linear map to these vectors to get vectors here, d phi P V1 to d phi P Vk. And then I apply omega to these vectors here, right? Omega acts on tangent vectors in N. And so that will give me a real number, right? So that will define, therefore, for me, the pullback. So phi star omega at a point P applied to V1 to Vk, which are vectors in TPN. This is defined to be omega at the point phi of P applied to the vectors d phi P V1, d phi P Vk. Okay. So this, it's clear, because omega is multilinear and d phi P is linear. It's clear that this will be multilinear, right? And also alternating, because omega is alternating. All right. So this will define for me at each point a K multilinear alternating function, right? So therefore we get phi star omega. The pullback is a K form on M. All right. Yeah, so for example, if I have phi is equal to a map into Rm, phi 1 to, or some Rk, well, okay, so into some Rm, sorry. Phi is equal to phi 1 to phi m from n to Rn, okay, and I take omega, which is let's say a K form on Rm, so it will be of the form a I bar, sum over I bar, a I bar d x I bar. This is let's say a K form on Rm. What will the pullback of omega be under phi, right? So if I look at phi star omega at a point P applied to vectors V1 to Vk. This is going to be omega at phi of P applied to d phi P V1 d phi P Vk. Okay. So this is sum over I bar. So ai bar dxi bar applied to these k vectors. So I mean this at the point phi of P. So what I'll get is ai bar of phi of P, right? And then what I'll get is dxi1 wedge dx ik, right, applied to the vectors d phi P v1 d phi P vk. And what is d phi P of v? What is this? This is a vector in Rm, right? Because phi maps to Rm. So the derivative is a linear map from TPM to Rm, right? So d phi Pv will be the vector d phi 1v up to d phi m v in Rm. Okay. And when I calculate this wedge product applied to this k tuple of vectors, remember what the wedge product is. It's the alt applied to the tensor product. And remember what the tensor product of these is. The tensor product will basically apply each one form here to each vector here, right? So what happens when I apply one of these dxi's to one of these d phi P vi's? What will dxi applied to d phi P VB? What will this be? If d phi PV is this vector in Rm, what is dxi applied to this?
Just by the coordinate.
It's just the ith coordinate, right? So it's just going to be d phi I V, right? Is this clear?
Yes.
Yes. So when I calculate this wedge product, what I'll get is basically products of these d phi i's, right? And then I apply alt to that. So you can see that what we'll get in the end is nothing but, so I have this ai bar of phi P, and then what I'll get is nothing but d phi I1 wedge d phi ik applied to V1 to Vk. Is this clear?
Yes.
Okay, using this equality star here. Okay, so by star. Okay, so what does that tell me? That tells me that phi star omega applied to this k tuple V1 to Vk is the same as this differential form, summation over I bar, ai bar composed with phi, into d phi I1 wedge d phi ik applied to V1 to Vk. So therefore, phi star omega or maybe I should write it this way, phi star of sum over I1 to Ik A I bar dx I1 wedge dx Ik is equal to sum over I bar A bar composed with phi. Okay, so this is a function on M, right? Into d phi I1 wedge d phi Ik. Okay. Is this clear?
Yes.
Yes.
Okay, so in particular, for example, if phi is equal to a chart x1 to xn from U in M to Rn, then phi star of a K form in Rn, sum over I bar AI bar dx I bar, this will be equal to sum over I bar AI bar composed with phi into so these phi i's are just going to be xi's here. So I'll get just dx I bar. Okay. So, I mean, I'm abusing notation here. In the left-hand side, these dxi's, these mean the coordinate functions on Rn, right? The differentials of the coordinate functions on Rn. Whereas on the right-hand side, these dxi's, these mean the coordinate functions on M, on the chart in M. Is it clear? So I'm abusing notation here. All right. Okay, this dxi is for the coordinate functions in Rn. This dxi bar is for the coordinate functions in M. Is it clear?
Yes.
Okay, so this thing is a K form in Rn, and this thing is a K form on the chart U. Okay. So what does this tell me? This tells me that locally in a chart, any K form on the chart U, see any K form on the chart U, I can write in this form, right? As AI composed phi summation AI bar composed phi dxi bar for some suitable choice of functions AI bar, right? On in Rn, right? Yeah. So if V is equal to phi of U, the image in Rn, right? Then if I look at the pullback, phi upper star, this gives me a linear map from K forms on V to K forms on U. Omega goes to phi upper star omega, right? This is an isomorphism. Is this clear?
Yes, sir.
Okay. This is an isomorphism. Okay. What that means is any, so this is onto, so that means any K form on the chart in M is equal to the pullback of some K form in Rn, and that K form is unique because this map is 1-to-1. All right. So for every K form on U, there is a unique K form on V such that the K form on U is equal to phi star omega. All right. Is this all right? Yeah.
Yes, fine.
Yes.
Okay. So now what we want to do, the idea is we want to integrate K forms. Okay. So what do we integrate along? So, I mean, normally in your measure theory integration, you're used to integrating measures, right? So measures you integrate over subsets of the space, of your measure space. Here we have to do something a little different. So, so what do we integrate forms along? Well, let's start with the simplest example, which is one forms. Okay. So I have my manifold, say, N. And I have a one form, which means at each point, I have a linear functional on the tangent space, right? Now, how do I integrate such an object? Well, the natural thing to integrate this over would be smooth curves in N. So suppose I have a smooth curve gamma. From an interval AB into M. Okay. Then what can I do? Well, for each point along the curve, I can look at its tangent vector. Now the tangent vector is an element of the tangent space here, and I have my one form. My one form acts on tangent vectors, so it will act on this tangent vector and give a real number, right? So therefore, I will get a function along this curve, right? That means I'll get a function along the interval AB, and then I can just take the integral of that function over the interval AB, right? So omega, if it's a one form in omega 1n, this can be integrated along C1 curves, gamma from AB to M. So what you do is you define the integral of omega over gamma. You define this to be the integral from a to b of the function omega at the point gamma t applied to the tangent vector gamma prime t dt. Does this make sense? Yeah.
Yes.
Okay, gamma prime t is an element of the tangent space at the point gamma t. So this is gamma t. And this tangent vector is gamma prime t. And so omega at gamma t will act on this to give a real number. You get a function of t, and it's easy to see that's a continuous function of t. And then you integrate that dt from a to b. Okay. So, and what's a natural example of one forms? For example, from physics, an example of one form will be integral of a one form will be work done along a curve. So suppose you have, say, f equal to, let's say a vector field PQ, a vector field on R2, let's say. Okay, so a simple example. Okay. So this is a vector field, and you think of F as force. Okay, this is a force field. So it could be gravitational force or electromagnetic force. Okay. All right. And so I have this force field now in R2. And if you remember your physics, then suppose I take a smooth curve now in R2. Okay. This is my curve gamma. All right. So if this is a small portion of gamma, and this is the force field at the point gamma of t, then what is the work done in moving from, say, a point p to p plus delta p? So this vector here is delta p. This vector is f. So the infinitesimal work done is so what is work done? It's force into displacement, right?
Displacement. Yeah. Just
So
a dot product.
the component of the force in the direction of the displacement, right? So this will be F dot delta P, right? Okay. And to get the total work done when you move along a curve, so the total work done along gamma, you get by integrating these small contributions, these infinitesimal contributions to the work done. So this will be the integral over gamma f dot ds. Right. Now, what does this mean? What this means is the following. This is actually the integral of a one form, omega sub f over gamma, okay, where omega sub f is a one form associated to the vector field f, omega sub f of a vector v. So, okay, let me just call this omega sub f equal to omega. This is a one form on R2. Okay. What is the value of this one form at a point P acting on a vector V? This is nothing but the, so I'm using dot product. So the inner product or the dot product of the vector F at P dot V. Is this clear?
Yes.
Okay. So this work done is nothing but the integral of this one form over this curve omega. Does this make sense?
Yes.
Yes.
Yeah. So I mean, if you wanted to evaluate exactly, what would this dot product be? This would be f is given by a pair p comma q, capital P comma capital Q. So this would be so the integral of omega over gamma. What would this be? This is the integral a to b of omega gamma t applied to gamma t. So now let's say gamma t is has coordinates xt, yt. Okay. So gamma prime t is x prime t, y prime t. Okay. And what is this one form omega? This dot product will be basically P, capital P at the point, okay, into X plus capital Q at the point P into Y, where V is equal to the vector XY. Okay. So omega as a one form, what will it be? Omega will be capital P dx plus Q dy, right? Because dx acting on V is the x coordinate x, and y acting on V is the y coordinate y of V, right? So this is the same as P dx plus Q dy acting on V, right?
Yes.
So omega P dx plus Q dy. Okay. And so this integral will become P at the point gamma t into x prime t plus Q at the point gamma t into y prime t dt. All right. And so this is also the integral of over gamma. This is what is defined in maybe in school, this, right? This is defined to be the line integral P dx plus Q dy, right? As defined.
Yes.
Okay.
Right.
Okay. Okay, so there's just a minute left. So let me stop this meeting and we'll start again. Any questions about this? This is just a basic example from physics. So work done gives you an example of a one form.
Sir, so in all this, we just require gamma to be C1, right?
Right.
don't even need
C1
smooth
is
maps.
enough. No, we just C1 is enough. Yeah, just C1 is.
So essentially, we are just integrating gamma upper omega.
Yes, that's right. That's right. That's right.
So,
That's the definition we'll come to. Yeah, that's correct.
Okay. So we don't even need smooth functions to define this
For
phi
pullback,
upper.
no, for the pullback, you just need C1 functions, C1
Okay.
maps for the pullback. Yeah, you just need C1.
Okay, fine. Okay.
Yeah. Okay, so let me stop this and we'll start again. Okay. Okay, all right. Now, can you, so this gives us an example of a one form in R2. Similarly, a vector field in Rn will give you a one form in Rn, right? Yes. It's just dot product with the vector field will give you a one form. All right. Can you think of an example of a two form in R3? Anyone? Coming from physics, let's say a physical example of a two form in R3.
Cross product of vectors.
Right. So cross product. So physically, what will that represent?
Area with sign.
Area is geometric. I'm asking for a physical interpretation. So a two form, like a one form, we integrated over a curve, right? Yes. So the one form is giving me the work done along the curve. If I have, so suppose I have a vector field, I think of it as a force field, right? Now,
right.
So one forms I integrate along curves. So it's natural to think that two forms I should be able to integrate along surfaces, right? Along a parametrized surface, right? Now, associated to a vector field and a surface, what is a physical quantity associated to that?
Normal to
amount
the
of vector field passing through.
It's the flux, right?
Flux, yeah.
It's the flux of the vector field through the surface, right? How much of the vector field is flowing out of the surface? So the flux will actually give me a two form. So let me explain that. One second. Yeah. So flux of a vector field in R3 gives a two form in R3. Okay, so what does this statement mean? Well, it means the following. So now I take, instead of a curve, which is a map from, let's say, the interval 0, 1 into R3, I take a parametrized surface or a parametrized cube, which is a C1 map from the unit cube in R2 into R3. So let me just call it C. My notation for these will be C. Okay. So C is a C1 map. So this is mapping into some surface in R3, right? So this is C of 0, 1 squared. This is a parametrized surface in R3. Now I have my force field F, and I want to see how much is flowing out of the surface, right? Yeah, how much of the vector field is flowing out of the surface? That will be the flux. So how do I measure that? Well, it's basically going to be the component of F in the direction of the normal vector to the surface, right? And how do you get the normal vector to the surface? You take tangent vectors to the surface, right? Take their cross product and then take the dot product with F, right? Yes?
Yes, sir.
Okay. So so this will give me a 2 form, omega equal to omega sub F. So omega at a point P acting on a pair of vectors V comma W. This is going to be F at P dot product with V cross W. Okay. So this is basically, you think of an infinitesimal parallelogram with sides V and W. And I have here F. And here I get the normal vector, the cross product, right? So this gives me basically the flux through an infinitesimal parallelogram with sides VW. Does this make sense?
Yes, sir.
Yes, sir.
Okay. So now if I want the flux through the whole surface, right, I should integrate the flux over these through these infinitesimal parallelograms, right? Yes. Okay. So
Yeah.
how do I get these infinitesimal parallelograms? What I can do is I can divide up my domain into very small squares. I divide my domain
Yes.
into very small squares. And now the images of these will be these very, very small parallelograms, right? Okay. And then I sum up the flux for each parallelogram, right? So what I'll get is an integral. So what will the contribution of each parallelogram be? It will be basically omega at a point. So if my point here is say x belongs to 0, 1 squared. Okay. So then basically I'll look at omega of at the point C of x, right? And I will apply it to the vectors dcx e1, dcx e2, right? Those are the sides of the square here. So under the derivative, those map to the sides of the parallelogram here, right? Then I apply omega to get the flux through this parallelogram. And then so this gives me a function of x, which is a variable in the unit square. Then I integrate this over the unit square. dx1, dx2. Does this make sense?
Yes.
Okay, so this will give me the flux through the surface S equal to C of 0, 1 squared. Okay. Yeah. So flux of a vector field gives you a 2 form in R3. Okay. So this is something, I mean, it has a physical interpretation. The a 2 form in R3 you can think of as a flux. All right. So yeah. And what is this thing that I'm integrating here? Well, this is nothing but if you now recall the definition of pullback, this is C star omega at the point X applied to E1, E2, right? dx1, dx2. Yes?
Yes.
Yes, sir.
Okay,
Yes.
so I mean, if you go back to the earlier example, as Orkojit was saying, for a one form, this this integral of a one form over a curve, this thing here I can also write as the integral a to b of gamma star omega at the point t applied to E1 dt, right? Yes?
Yes.
Okay. Because I mean, E1 means the basis vector 1 of R. Okay. Yeah, and d gamma t of E1 is just gamma prime t, right? So this is the same as this, all right? Okay, so now this leads us to the general definition of integrals of k forms over what are called singular k cubes. So singular k cubes will be the higher dimensional version of curves. Okay. So I mean, a C1 curve is a map from a C1 map from the interval 0, 1 into my manifold M. Similarly, a singular k cube, that will be the k dimensional version of a curve. It will be a C1 map. So a singular k cube in M is so yeah, I mean, I can take it to be smooth, but I don't need, I just need a C1 map actually. Is a C1 map C from the unit cube 0, 1 to the k into m. Okay. All right. And for omega a k form on m, we define the integral of omega over this singular k cube, okay, to be just the same integral that we have above here. So it will be the integral over 0, 1 to the k omega at c of x applied to dcx E1 up to dcx ek dx1 dxk. Okay, so this is the same thing as the integral over 0, 1 to the k of c star omega at the point x of E1 to ek dx1 dxk. Is this clear?
Yes, sir.
Yes, sir. Yes.
Okay. So this function here, c star omega at x applied to E1 to ek, what is this function? See, note that if I look at the form c star omega, right, this is a k form on Rk, right? It's a k form on the unit cube in Rk. So that means that c star omega, this is equal to some function h times dx1 wedge dxk, right?
Yes.
H is a continuous function on the unit cube. Okay. And how do I get this function h? Well, I take a point x in the cube and I look at the vectors E1 to Ek at x, and I apply both sides to those basis vectors E1 to Ek. So then I'll get c star omega at x applied to E1 to Ek. This is equal to h of x dx1 wedge dxk applied to E1 to Ek. And this is just one, right? Because this dx1 wedge dxk is just the determinant in Rk. So it's the determinant of the matrix with columns E1 to Ek, that's the identity matrix. So determinant of identity, this is 1. So this is just h of x, right?
Right. Yes.
Okay, so this function that I have here, this is nothing but h of x. Okay, this function that I'm integrating is nothing but h of x, where c star omega, h is just the coefficient of c star omega. Okay, c star omega is h dx1 wedge dxk. Is this clear?
Yes.
Okay, all right. now we can do the following. So we have these singular K cubes. So like in your algebraic topology, when you define homology, right, you look at singular simplices, right, in your manifold or in your topological space. And then to define homology, you define the space of chains, right, of singular chains. So that is the free vector space on the set of singular simplices. So similarly, here we can define the space of singular K chains in M, C sub K of M. This is defined to be the free vector space on the set of singular K cubes in M. So this is, remember, the space of formal sums summation I goes from 1 to M, alpha I Ci, where n is greater than or equal to 0, alpha 1 to alpha m belong to R, and C1 to Cm are singular K cubes in M. All right. Okay. So for a singular K chain, sigma equal to summation alpha I Ci and K form omega in omega K of M, we define the integral of omega over sigma to be the sum over I integral alpha I integral omega over Ci. All right. So just omega is defined, the integral of omega is defined over the singular K cubes, which form a basis of the space of singular K chains. So you have a function on a basis, it extends uniquely to a linear function on the free vector space, right? Yes?
Yes.
Okay. All right. So so then what does this give us? Therefore, each omega, a K form, gives what's called a singular cochain. Integral of omega, which is an element of the dual space of the space of K chains. So integral omega this is a linear functional from CKM to R. Sigma maps to integral of omega over sigma, right? This is a linear map. I mean, this is a linear function, right? This is linear in sigma. Okay. Yes, is this all right? Yes.
Yes, sir.
Yes, sir. Yes. Yes,
So now we get a map, therefore, we get a linear map phi from the space of K forms omega Km to the space of singular cochains CKM star. Okay, so into the dual of the space of chains, omega maps to integral over omega, integral of omega, right? Yeah.
yes.
Yes.
Now, the claim is that this map is actually one-to-one. In other words, if integral omega over all k chain sigma is 0, then omega is 0. Okay, so that means omega, we want to say any k form is determined by its values over, by its integrals over singular k cubes. Okay, so this means that there should be some way to get back the values of omega acting on tangent vectors from the integrals of omega over cubes, right?
Yes.
So how do we get back? So suppose I take a point P now, and I have tangent vectors at P, say V1 and V1 up to Vk, right? This is my point P. So I take a point P in M, and I take V1 to Vk in TPM. Okay. Somehow I want to get the value of omega acting on these vectors from integrals, right? So what's the idea? Well, the idea is, suppose I was to take a sort of a cube in M, which is almost parallel to these vectors V1 to Vk, right? Then we should expect the integral of omega over this small cube. This should be, well, if the lengths of the cube are of order epsilon, then this should be something like epsilon to the power p into the value of omega acting on the vectors V1 to Vk, right? Yes. Okay, so what we're going to do is the following. Is you take any singular k cube C, all right? So C is singular k cube. Such that C0 equal to P and the derivative of C at the origin maps EI to VI. Okay, I equals 1 to K. Okay. Now C could be some big cube like this. Okay. This could be the image of C. Okay. Now what I want to do is get a small cube out of C. So how can I do that? Well, what I can do is I can restrict C to a very small cube sitting inside the unit cube of side lengths epsilon, right?
Right.
So in other words, what I want to do is I define a cube C sub epsilon of x. Okay, this is defined to be C of epsilon x. Okay, x belongs to 0, 1 to the k. So the image of C epsilon will be this small cube, this small singular cube. Okay. Now what happens if I integrate omega over the small cube? So I need to calculate then C epsilon star of omega, right? So for that, first, let me look at the derivative of dc epsilon. Okay, so the derivative of dc epsilon at a point x applied to the vectors ei, what will this be? So by the chain rule, this is going to be the derivative of c at the point epsilon x applied to the vector epsilon times ei, right, by the chain rule. Okay.
Yes.
And this is linear, so this is going to be epsilon times dc at epsilon x acting on ei. Okay. So therefore, if I look at the integral of omega over c epsilon, then this is going to be integral over 0, 1 to the k. So omega at the point c epsilon of x, so that's omega at the point c of epsilon x applied to dc epsilon at the point x of E1 up to EK. So that will be epsilon dc at epsilon x E1 up to epsilon dc at epsilon x EK, right? Dx1 dxk. Yes, but now omega is multilinear, so these epsilons will come out, right? So I'll get an epsilon to the k coming out, and then I have this integral 0, 1 to the k omega of c of epsilon x into dc epsilon x E1 up to dc epsilon x EK, okay, dx1 dxk, right? So you see that the integral over this small cube, it's of order epsilon to the k, right? Yeah. So as epsilon tends to 0, if I want to get a finite limit, what should I do? I should divide by epsilon to the k, right? So I take 1 over epsilon to the k. So then I get a 1 over epsilon to the k here, and then I'll get a 1 over epsilon to the k here. So these two will cancel, right? And then inside, what do I have here? This thing, this is a continuous function of x, right? This is a continuous function of x. And this converges. What does this converge to as epsilon goes to 0? This converges to omega of C0 dC0 E1 up to dC0 EK, right? as epsilon tends to 0? Yes?
Yes.
Yes, sir.
Okay. And the convergence is, it's easy to see this is uniform. And this is nothing but omega at P applied to V1 to Vk. Right? So therefore, the whole thing, this epsilon to the k cancel. The whole thing converges as epsilon tends to 0 to omega P applied to V1 to Vk. Right? So therefore, we've got the value of omega at an arbitrary point P acting on an arbitrary k tuple of vectors V1 to Vk in terms of the integrals of omega over cubes, over small cubes, right? Yes. So thus, omega P V1 to Vk is equal to limit epsilon tending to 0, 1 over epsilon to the k, integral of omega over c epsilon for any singular k cube c such that C0 is P and DC at 0 applied to EI is VI. I goes from 1 to K. Is this clear?
Yes.
Okay.
Yes, sir.
So thus, if the integral of omega over c is 0 for all k cubes c, then omega is identically 0, right? From this above formula, because the right hand side vanishes then. Is it clear? Okay. Yes?
Yes.
Yes, sir.
So what do we have therefore? Therefore, we have that this linear map from the space of K forms to the space of K cochains, CKM star, this is 1-to-1. Okay, so we can think of the space of K forms as a subspace of the space of cochains. Okay, this embeds into the space of cochains. All right. So this K forms embeds into K cochains. Is this all right?
Yes, sir.
Okay. Okay, so fine. Okay, so we're almost out of time. So in the last minute or so, any questions about this? Any questions, comments? Okay, so a K form is determined by its integrals over K cubes. Okay. So we can recover it from its integrals over K cubes. Okay, by taking the integrals over small cubes, C epsilon, and dividing by epsilon to the k. Is this all right?
Yes, sir.
Okay, so if there are no questions, then let's stop today. And I'll see you next week. All right. Okay.